Good. So we are very happy to have Tatevik with us from the US today, and she's going to talk about some monetary policy issues, which are very timely, I think.
We hope so. Thank you all for being here. It's very good to see, faces I haven't seen for a long time online, and I hope to see you this summer somewhere. And I'm also delighted that Julia is online because she's going to try to help me answer the hard questions. So the title is Networking Yield Curve Surprises, Implications for Monetary Policy. This is joint work with Tatiana Dalhouse at the Bank of Canada and Julia Schemberg, and she's online. Tatiana is probably going to join at some point, but then might not be able to stay for the whole presentation. So this is as we can get. Let me actually give you a little bit of the motivation, but just to do fairness to the paper, there is like the monetary policy part, but there's also the econometrics part, and I think the econometrics part, deserves attention on its own. So if you want to think about it in a different context, please feel free to do so, and then we can discuss further. But we were inspired a bit with monetary policy going into this project. So I started with a quote from Chairman Bernanke. This is about like 2 decades ago. And all of you, some of you are in a central bank, so you would appreciate that, monetary policy has both short run and long run aspects. We've seen this with, unconventional monetary policy quite a bit. And then, the quote that actually says, because the values of long-term assets are affected by the whole trajectory of expected short-term rates, it is even more vital that information relevant to estimating that trajectory be communicated. So why do we put this quote in there? Because we would like to think about different aspects of monetary policy. And then, like a broader context in the literature, essentially the sensitivity of the long-term rates to the short-term interest rates, it's highly debated, it's time varying. Then there is this part of the literature that says, perhaps like market expectations and survey expectations behave differently, and those are equally important for monetary policy making. So what we do essentially look at the sensitivity of the interest rate surprises at different maturities, but from a survey point of view. So we're going to look at subjective yield curve surprises. Again, so why does this matter? So we're going to introduce a flexible time varying network model to trace the propagation of interest rate surprises across these different maturities. It matters because we can actually talk about various aspects of monetary policy, but we can talk about them jointly. More specifically, we can think of the conventional monetary policy, which is essentially interventions or unexpected movements in the short end of the yield curve. Unconventional ones, which could be, unexpected movements on the long end of the yield curve or somewhere else. So we're not going to explicitly talk about quantitative easing in terms of quantities, but we will talk about interest rates, the yields associated with these quantities. And thirdly, we would like to bring in this forward guidance into play, this communication, as the quote was highlighting, and just try to quantify, what is the role of this and how does that affect the sensitivity of the interest rates at various parts of the yield curve. So, the way we think about this is that forward guidance and overall market conditions can actually affect the intensity of this network, and that's why we like this network approach to the question. And for instance, I hope by the time I'm done, some questions that you can answer would be: do monetary policy surprises, let's say deviations from expectations of 3-month rate or 5-year rate, do they spill over to different maturities differently? Okay, so is there any difference whether the Fed intervenes on the short end or on the long end, and what is the role of the forward guidance in actually affecting these spillovers? So I think with Helene, we agreed, like, if you guys have questions, you just ask, right? So please do so. Okay, so the contributions of this work is essentially methodological. So we have this dynamic econometric model that can allow for unknown and potentially asymmetric contemporaneous spillover matrices. And this asymmetric and unknown are the keywords. So in that sense, we actually extend the econometric literature. We show the model properties and identification via simulations. And from economics point of view, essentially, we introduce this joint modeling of the interest rate surprises at different maturities, and can speak to this interest rate sensitivity literature that I was alluding to. Also provide a framework for assessing how different dimensions of the monetary policy come together, and then what we can learn in terms of the policy implications from this. Okay, so the broader literature, I'm not going to go through every single one of these papers, and I'm pretty sure I've missed some papers that are relevant here, but essentially from the methodological point of view, so we actually relate to this spatial weight matrix estimating literature, so we have a contribution in this respect. So we have this time varying aspect of the network. So there's a vast literature in that. So we actually borrow a lot from those. And then, we have this monetary policy and interest rate surprise literature that I already talked about. Okay, so
can I ask just a clarifying question?
Yes.
So how do I think about the network? So is it, are you thinking about network of traders, a network of banks? Are we thinking about networks purely in terms of securities? I mean, what is the network exactly? Yeah.
Yeah. So this is a super good question, because to us it was very intuitive. So we started working on this paper. But then when you go to this literature, everybody has their own favorite term structure literature, term structure modeling framework, and there are all these issues with this. So, so I have it later in the slides, but I will say it now. So there is this recent paper, essentially by Gospodinov and Kramp. So they actually have this notion, that the overlapping nature of these maturities, right? Because it's interest rate at various maturities. So there is a commonality in those. This actually introduces this spatial type correlation structure in the surprises. So it's not necessarily like a physical network that we're thinking of, but more like from the duration point, the way these bonds are priced, so this could generate this network structure, and this is essentially what we're trying to capture. The innovation is that, we do this from the subjective point of view. So this is essentially on the surveys expectations and the implied forecast errors. And then the fact that we can actually, so we don't rely on the theoretical model to generate of how this would look like, even though that's possible from a theory point of view, as this guys showed in their paper. We actually get the data-driven or estimated weights, and then we can try to say like how the spatial correlations between these maturities actually looks like. So I'm not sure if I answered the question, but that's
thank you. Yes, I think Julia wants to add something. Yeah. Or Julia?
Yeah, no, just that the neighborhood.
Mm-hmm.
Can you hear me?
Yes.
Okay, fantastic. So just that the neighborhood is defined by maturities. So maturities that are close to each other are, for example, the short-term maturities are closer to each other than short and long-term maturities. So that's the idea. So we're basically ordering according to the maturities.
Okay, and the liquidity doesn't play a role. So you could have adjacent maturity, one very liquid, one very liquid. It's not.
So in principle, it could play a role, because we could get we could get a data says these maturities are very closely related to each other, but we would then have to go and try to figure out why that is the case. So at the moment we have, we model this network structure. There is a commonality between them. This network intensity can affect all of them. And we do have some parameters determining this network intensity. Liquidity is not one of them. So that's potentially one other thing that we should consider. Yeah.
Sorry, can I jump in also with a question on this? So do you have a prior?
Could you speak a tiny bit louder, Sylvia? Yeah, if you can.
Hi, sorry. Yes, sorry. Can you hear me now?
Yes.
Yes. Okay. So the question was, do you have a prior for what? I suppose the question is, do you impose a structure on the network ex ante, or do you sort of let the data pick up the relevant links, and then based on those links that show up, you sort of have a narrative for that?
So we don't have a structure, so they're unrestricted. I mean, we have some restriction in terms of trying to make sure the system is stable, you know, so this type of restriction, but we don't have a structure on the weight. So whatever,
Okay, so
it's purely data driven. This is what we estimate. It's actually interesting. But again, so, you know, when we estimate this, then people are like, oh, so which term structure model can generate something like this? So, you know, this is where we actually were a little bit comforted that there was this paper recently that came out in Econometrica showing that these structures can arise in very natural settings. So, you know, that basically helps us say that we are not, you know, that, you know, it's actually justified from the finance literature point of view.
Yeah, no, but like just going back to the liquidity point, I suppose then the liquidity is not directly modeled, but it could be one channel through which these links show up, right? Yeah,
that's right. So hold that thought for a second. Then, you know, the moment I go to the explicit equation, maybe I can like suggest where we potentially can consider liquidity, which we don't at the moment. Yeah. Anything else? Okay, so I will do a little bit the econometric model again. So I would like you to think about this broadly. So if you don't want to do the monetary policy application, there's still some, you know, value to this, particularly with the banks going down in the US. You can think like, you know, there's some network effect and spillover effects in those contexts. So could be direct application there. So, you know, I approach this problem. So Giulio has worked on spatial models quite a bit. So I approach this more from time series perspective. So the slides are more like my journey of how I learned about this literature. So let me walk you through this. Okay. So typically, I mean, the way these spatial models work, I mean, so you have a variable y for a unit I at time t. These are connected for the same variables for different j units at time t. And then, you know, there is this notion of weights that actually will direct these contemporaneous correlations. Okay, what do we have on top of this? I mean, so this is a dynamic thing. So there's also this rho t, which is going to be the network intensity. This can affect these correlation structures. We're going to have a law of motion for this. And this will be important to model some of these aggregate things that are happening. Okay, so it's lag model, but you don't see any t-1s here because it's a spatial lag, right? So like this is a lag in the spatial dimension. At least that's how people typically thought about this. So you could actually think, I mean, the classical examples could be, you know, one state, how is it related to another state in terms of trade volumes or, you know, distance or this sorts of things, right? So we're taking it to a very different context at the moment. Okay, so then we have controls, which are going to be unit specific. So XIKs, time t. So there is this notable thing here that we have a parameter beta, which is not indexed by I. So hold that thought, and then I'll say a little bit more because this is going to be super important for identification. But essentially, I mean, this is the dynamic spatial lag model. So again, rho t is going to be the network intensity. This weights our innovation over the literature would be that these are going to be assumed to be unobserved and also potentially asymmetric. So they're not going to be, I mean, they could end up being symmetric if the data wants it to be, but they're not going to be imposed to be symmetric. Okay, so unit I can be connected to unit J differently than unit J to unit I. Okay, so and then what? So I can write this in a matrix notation. So, you know, then everything is collapsed into matrices and vectors. So this basically is a spatial lag dimension. As a time series person, you know, what I would do saying, oh, yeah, wait, I mean, I can rewrite this. And if I rewrite this, you know, I can say Y is related to some controls, you know, and then there is this reduced form variance covariance matrix, which actually directs this contemporaneous correlations. And this is something that the VAR literature borders with all this time for all this years. So, you know, what's so special about this, right? You know, in some sense, I mean, they're similar, and one can think about, you know, like making these two types of models closer to each other. But what the spatial literature likes about this specification, right, is that, you know, I mean, this inverse can be written as infinite sum. So, you know, you could rewrite this, and then I can make it obvious that this is a highly nonlinear specification where x's and the error terms, they can affect y. you know, not linearly. I mean, there are all these powers hanging in there, and they can make a big difference. Okay, so they can make a big difference in terms of propagation, but also like whether the same size of the shock can generate the same type of magnitude or not. So fine, I mean, so this looks like something doable, you know, perhaps we can do this, but then where do I get the identification? So where is the magic, right? So we care about this W. Now this W is going to be in this variance covariance matrix. I still need to, so rho is going to have a law of motion on itself, so that's not necessarily a problem. But this W, I mean, okay, so in the VAR, I mean, we just say, oh, now I need to impose enough restrictions so that the variance covariance matrix, which is symmetric, can talk about this W, right? So if I impose symmetry on W, I don't have a problem. I'm back to the same like Cholesky type decomposition setups, but we don't want to impose this. Okay. So yeah, and I should mention, I mean, so here, Sylvia, so this is kind of to your point. I mean, there are some restrictions on this model, but mainly to guide to make sure that the, you know, the system is well behaved.
So,
okay.
So why do you absolutely don't want symmetry? I mean, what's your prior on?
So, I mean, what we would like, okay, maybe, I mean, it's a little bit related to your liquidity story, right? Although we don't model the liquidity per se, but, you know, the notion is like, you know, one market is there's a segmented market type notion, right? That something happens to this market, maybe propagates to the other one in a particularly different way than, you know, the other way around, if there's no frictions in that, you know, let's say medium term or the long term maturity market. So that was a little bit the notion here, that you don't necessarily want to impose symmetry, but you could get symmetry if the data wants it to be symmetric. So that was our thinking here.
So it's a kind of arbitrage restriction, I mean, some arbitrage issue or some.
Exactly. Exactly. Or failure of it, I guess, you know, because, yeah. So that somehow, like, you know, there's a segmentation. So there is this notion of preferred habitat type models. I mean, they all kind of go to thinking about it like that. So that was a little bit why a priori, at least, we didn't want to restrict it. Okay, so yeah, so this weight. So let me say a little bit more before, like, I get into like where we get extra moment conditions for identification. So these are the spatial weights again. So, you know, unknown, asymmetric potentially. So there is a normalization restriction that the diagonal is 0. But then overall, you know, we impose a weight interpretation on this. So it's going to be between 0 and 1. The way we achieve this is through this multinomial specification, so that D is actually freely estimated, but then the implied weights actually live in the space that we would like them to. And again, so this is basically repeated. So there is a maximum eigenvalue restriction to make sure that things are stable. Okay, so how do we get identification? So that's like kind of the last bullet, and then I have another slide, is this pooling, okay? So this beta didn't have an I subscript, so essentially these are unit-specific covariates, but we pool through them. So because we are going to pool through them, so pool through this weight. Okay, so I have an example here, right? So like if rho was equal to 1, so this is essentially what I would have. We're back to the problem that if I want to identify W from variance covariance matrix, you know, I have symmetric variance covariance matrix, so that's not going to help me to do this asymmetry. But this pooling across variable specific regressors is going to generate more orthogonality conditions. So in the specification that I will show, at least in the results, I mean, essentially things are over-identified because we literally pull through all the unit-specific regressors, but you can think about pulling them separately as well. Okay, so maybe, you know, there's some concentration in one part of the yield curve versus the other one.
Sorry, Tatevik.
Can I just ask one thing first?
Sure.
How this compares to an Elsa and Siegel model, in which when you go to the cross section, you have that weights that vary with one specific parameter? Is actually some explanation weights.
Yeah, so Nelson and Siegel, I mean, so they have the 3-factor, and then there's
but the W is in the cross section, right? Can I think the W is in the cross section? Yeah, in the cross section they have these very specific weights that depend on the parameters.
That's right. So, you know, like we could go back and actually compare this. But Nelson and Siegel, so basically they have the short term like loading on one and then medium loading on the other factor and so on, right? So there's like literally the clustered interpretation. So we don't have that, again, a priori, it's not imposed like that, as Sylvia was asking earlier. So it's not like there's something in the weights that would say only the short terms, like the short terms are supposed to be clustered together and the mediums are supposed to be clustered together, okay? They can end up being, you will see that that's, not necessarily the case, but they can end up being, but that's not imposed.
But this modeling could encompass something like that.
So that's something we could do, like, so at some point we did this, like, we estimated a Nelson-Siegel type model on our surprises. So Julia, now I cannot remember, like, what the result there was. But again, so like we could try to like, sort of simulate from Nelson-Siegel type setup and see what we pick up. That we can try to do. We have not done that.
Okay, thanks.
Because I mean, your question is like, if that's the true structure, can I pick it up, right? I mean, so that's the notion. Yeah, I think when we played with that specification was more in the empirical context, so we did not try to do it in the context of Monte Carlos or.
No, I mean, in a way, what we have is a nonlinear one-factor model, right? So the rho t could be interpreted as a latent factor that is very flexible in the sense that it can pick up a lot of. It brings time variation in, and it enters a nonlinear model, or it enters nonlinearly, and then the double and how it enters is then determined by the W, which also enters nonlinearly. But at the end of the day, it's only one factor. So in that sense, I could imagine that it is possible to get some richer dynamics with a multi-factor model. So I'm not sure if it would be possible to pick up exactly the stuff that could come out.
But it could be approximation then. And I guess I can clearly see this is richer in terms of flexibility than that model. It's just to give a notion what the model can capture. Thank you.
And I mean, this notion, I mean, just to pick up to what Julia said, I mean, you will see that at the end, I mean, perhaps you would come back and ask us to have two different rows and two different dynamics, so in principle, that could be extended in that dimension. Yeah.
Sorry, can I also ask something to clarify? So what you said is that the object of interest is to identify the weights. And you don't, so let me see if I understood. And you don't want to necessarily use restrictions from the variance covariance matrix because you don't want to impose symmetry. But what you do is to effectively pool across the covariates. What does that mean? Like using combination of interest rate surprises in your cases, like restrictions on subsets of combinations of the. Is that the right way to think about it?
So these are going to be the interest rate surprises, and these are going to be covariates that are specific to maturities. Okay, so in the practical implementation, we're actually going to use the lagged realized interest rate changes for particular maturities as instruments. So this is essentially an instrument, if you can think about it like this. The notion is that surprises are predictable, and if they are predictable in a similar way, in the sense that can justify the pooling, I mean, so that actually generates more conditions that we can actually try to use. So you could, this is very application specific. So in the context of the particular application, I mean, you worked on this, surprises are predictable. so we kind of utilize this aspect, but again, so the pooling still has to be justified further.
Yeah. Okay, thank you.
Yeah, so the restriction is that they are predictable in a similar way. Yeah. Okay. So hopefully we're good. I mean, so this is like the important dimension, identification. So the dynamics, I mean, this basically we borrow from the work that Julia has done before. So this is going to be in the context of this generalized autoregressive models. Yeah, so it's a data-driven way of modeling heteroscedasticity, essentially. So we're going to reparameterize rho so that it lives in the space of -1 and 1. And then, we're going to have a law of motion for this vector, as Julia was alluding to. So this is going to be latent vector that is driven by its path, potentially with some observables. And then the innovation to this is essentially the score. So it's the first derivative of the log likelihood with respect to FT. So what's good about this? There are many other ways we could have modeled the time variation in the row. The benefit of this is that, you actually have the likelihood in closed form, so you can easily do numerical maximizations to estimate the parameter. And again, so if you like more the Bayesian world too, I mean, having the likelihood in closed form actually is helpful there as well. For whoever wants to see how that looks like, okay? So essentially, this is the likelihood, the score, and then, there's like a whole literature justifying, the optimality of these updates, a la scores, so information theoretic optimality, and then you can ask more questions about this to Julia. So, Julia, did I do a decent job on this? Okay. All right. So that's the model. Again, so if you don't want to think about monetary policy, there are many other things you can think of, Again, so in the context of the banks, I mean, maybe one bank is not exposed to the other the same way as the A is not exposed to B the same way as B is exposed to A, right? So you can actually have implications and applied outcomes in those contexts. So, I'll show you a little bit the simulations of how exactly does this approach work, and then we go to the monetary policy part. Okay, so 2 Monte Carlo experiments that we've done is in the context of correctly specified model, and then, when we have a misspecification. So this is the data generating process for the correctly specified version. We we set the parameters to certain values. I mean, we draw the x's and the epsilons. So we have some combinations of n and t. So 7 would be more similar to our empirical specification. And then we're going to try to see how we do in this context. So here, the benefit of Zoom is that you can actually see my W's. If I was on a big screen, you probably wouldn't be able to see this. Okay, but these are the weights. And then these are the parameters that go into the law of motion of the row. The black vertical lines are the true values, and then we have the various shades or various colors going from green to red, and that green is smaller sample size and red is the larger sample size. So what we want to show here is that as the sample size increases, you basically you have the consistency notion. I mean, so you get closer and tighter to the truth. I mean, in the paper, we have a lot more exercises and like more formal treatment to understand how well we do. But the point is that, as you have the sample sizes become larger, both in cross-sectional and time dimensions, you actually get to the truth. So then, I mean, we have the misspecified version, a particular kind of misspecification. You can think of some others as well, where we actually specify this.
Sorry, can I ask one thing? So even the sample size, I mean, is this a way of saying that you're more likely to be successful with this model if you like to applications to financial markets where you have quite large sample sizes? Because if I think of a typical macroeconomic application, right? I mean, the sample is never going to be even 300, right? So in some sense, what's the or I suppose what's the relation between sample size and cross-sectional size? Like if I wanted to use this for a macro application, right?
So the notion is they can actually help each other. So cross-sectional aspect can also help you. So hopefully that's a relief from a time series point of view. So, we have like lots of exercises in the paper, but I don't think we formalize this, like what has to be the optimal like N to T ratio, but the direction is that both dimensions, like both increases in both dimensions are helpful.
Okay.
But you are right that, I mean, the more data you have, the better you will do. So
No, but like if you because
Yeah.
sometimes with VARs, I suppose if you have very few T, then if you have a lot of N, it's even worse. But in this case, if you have few T but you have a lot of N, it could be a good thing. Okay.
So we can actually
this is another sort of extra benefit of using this rather than a standard VR sort of.
That's right.
Yeah.
And Sylvia, just like to your point though too, like, so at the moment we are not modeling any lag dimension in the time series setting, so that's why we work with the surprises, because, that somehow helps abstract from, some of the issues that you are bringing up. But, you could imagine this being nested in a more typical time series setup too. And then, the issues will become more severe and different, I guess, too. Julia, did you want to say something? I thought you were, yeah.
No, just saying that the number. I mean, there is a kind of it's true that the accuracy gets higher when the cross section gets higher, but there is a limit to the cross section, which is kind of a little bit similar, I think, to the VAR, maybe a bit less severe, but I mean, the more cross-sectional elements are there, the more weights are to be estimated as well. Right, so it's there. So I think if the dimension of the n really wants to be large, then one has to think about using some sort of shrinkage to get the weights.
I mean, here it also helps that ROT scales everything, right? So like somehow your model can utilize that structure to capture the dynamics. Okay, so so some misspecification. So misspecification that I'm going to show you is in the context of like this network intensity parameter. So here essentially we say, okay, so what if you have this cosine type dynamics? What if you have a discrete break? What if you have a constant break? Could you pick up with the specification that we have? So here the black is still the truth, and then the red is the median of the empirical quantile. I mean, so we take this as a notion that we can actually filter this with reasonable accuracy. I mean, there's a little bit of a delay in picking up the discrete break, but we think the model works. Again, so you could think of some other, I think Anna's question was kind of to the direction, you could think of misspecification in the weights, and we can actually try to design a Monte Carlo in that setting to see like what we pick up and how we pick it up. So that we can do. Okay, so if I persuaded you that this all works, then I can go ahead and say, okay, so what did I learn about the question that I was curious about? Okay, so this is going to be yield curve surprises. Again, so it's the unexpected component. So we're going to jointly model the dynamics of this, allowing for asymmetric connections across these maturities. The dependent variable is survey implied surprises. So we go to this blue chip financial forecasts. I mean, it's nice because it actually has predictions for lots of interest rates. The particular one I'm going to show you today is essentially based on the 6 months ahead expectations. So the surprise is going to be defined as forecast error, essentially. So it's the realization minus the expectation. But I could have done it for different horizons. So this is the one we're going to show. So we have 7 maturities from 3 months to 30 years. So this pooling was super important because I don't get identification if we don't do this. So the lagged yield changes are going to be the variable specific covariate that we're going to pull through. Okay, so then fundamentals and forward guidance can affect spillover intensity. So given the questions that were asked, I mean, so presumably liquidity could be one of this, which we don't have here, but this is actually going to be a good way to think about.
Sorry, Tatevik, I was wondering this because when you have different maturities, does it make sense to have only the 6 months side expectation? I was thinking then you compute, depending on the maturity, you are computing the surprises.
So we could, I see what you're saying. You're saying, 6 months, I have different maturities that implies different horizon.
Yeah, exactly.
For each one of them. So we could actually do an implementation like that as well, like so essentially thinking about the forecast horizon as opposed to, because here forecast horizon is fixed, but in terms of this maturities, it implies a different leftover horizon, if you will, right? So we can do it in that context as well. I mean, we can do it like that as well. So here we basically thought, I mean, so if there is an innovation, I mean, all of these things get updated, right? I mean, and then if we fix like a particular horizon for which it's updated, can I think about the spillovers? But we could like definitely, you know, entertain thinking about this different horizons as well. So that, you know, it was just an easier analytical exercise, I think. But I see your point. Because again, there's an overlapping nature. So like, what exactly does that mean? If I forecast 6 months ahead, the 1 year maturity or the 2 year maturity, right? Mm-hmm. Okay, so the data that I'm going to show you, you know, that we're going to use, this also can be updated, but we didn't have a chance yet. So this is basically 1888. This is where I have the data from the survey, and then we stop in 2016 because then other things happen. So like, but we can go back and update the data. So, you know, on this. So. Was there a question? Or?
I just want to ask, what is the fundamentals in the previous slide?
So, okay, so we have IP VIX, IP, I think we have, hold on, I can tell you. So we have
so it's macro stuff that's supposed
yeah,
to
IP
move.
and VIX, and then, you know, the path factor we bring in as a forward guidance. But there you could do liquidity. I mean, so that's why I want to bring in the liquidity that you know, asking me before. Yeah.
Okay.
Okay. So again, so the relevance of this in the context of the yield curve surprises, people have used these models in different contexts. So we're bringing it to the yield curve literature. Again, so the notion is that this overlap of the neighboring maturities has the potential of creating this spatial structure, and then surprises are predictable. And to some extent, I mean, we also outsource this forecasting exercise to the blue chip folks, you know, so whatever is their favorite model for term structure, I'm sure that's what they use, right? So we abstract from that question altogether. All right, so what is the data? So these are the interest rate surprises based on the blue chip survey, you know, that we use. So here you can see all, you know, all the short rates are sort of short, medium are at 0. So at some point I should also show you the results before the 0 lower bound. The results that I have in the slides are going to include all the data. Okay, so the core, the main thing. Okay, so estimate these weights. Hopefully I persuaded you that this was a reasonable exercise to do. So this is how it looks like. So it's a network paper, so it has to have a graph, but I'll talk about the picture, about the table, okay? So the table, essentially the zeros are imposed by construction. Okay, and then the rest of the zeros is essentially what our estimation output implies. Okay, so they're rounded, I mean, they're numerically 0. So what is interesting here is that, you know, our estimation procedure wants this weight matrix to be sparse, okay? And then it wants it to be sparse in a particular way in that only the first off diagonal basically matters. And you do get situations where, you know, there is asymmetry, like 6 months is connected to 3 months differently than the 3 months is connected to the 6 months. So this is interesting. Again, there were no restrictions imposed, and this is essentially the result of the estimation. So what about this time varying spillover?
Sorry, so just the above the diagonal versus below diagonal, the asymmetry, can you say something about it? So it seems like one direction versus the other. So you go from the lower maturity to the bigger maturity. What's the? So
if I go from the so can we
6 months to the 3 months? Just
yeah.
pick and because it seems like, you know, the pattern is not fully the same. So
that's right. That's right. So the pattern is so you know, this thing basically kind of goes down, and I mean goes down, right? I mean, on the other hand, I mean, so this is I mean, it's not monotonic. I mean, so overall, like, you know, seems like it's going down, but you have like some situations where that doesn't obtain the pattern. Of course, I mean, here we are not showing you the estimation uncertainty associated with this. We don't know how to do it yet. So these are just the point estimates. So if I show you the estimation uncertainty, perhaps like, that would be more.
So you're saying we should not draw any conclusion from the point estimates, based on.
No, we should. I mean, that's all we have at the moment because we don't know how theoretically to do the inference on this thing yet. Okay, so this is what we have. But all I want to say is that potentially, I mean, I don't know if I want to take the 57 and 42 and say these are like dramatically, different from each other, and this breaks the monotonicity, right? So that's something that I don't want to say. But the fact that this is sparse and it's sparse in this particular way, I mean, this is, I think, something that we should take from this exercise, and I'm pretty comfortable with that. Yeah. So like the exact numbers, like, again, like, yeah, there is some uncertainty around this. So one should take it with caution.
Sorry, I know you said that we shouldn't take it, this literally, but then if I look at it, if I can think, can I think of it as sort of an impact impulse response function?
Yeah. So that's what I'm going to show you next. Because
right. So if I think of it as an impact impulse response function, what I think I see here is that effectively what this is saying is that if you move the short end, right, this is going to trickle down to longer maturities. So maybe you cannot take the numbers to give you a particular, but there's a switch in the order, right? So for example, if you look at the 6 months, the 6 months has much more of an effect on the 3 months than the 1 year. But if you look at the 5 year, it's the opposite, right?
That's right. So this is essentially, so I will show you at the end. So because again, this is just a weight matrix. There's also a row that amplifies these things or pushes it up or down, right? So at some, I'll show you the impact impulse response, if you will. And then, that has all the nonlinearities baked in. But the punchline essentially would be that intervention in the medium term has a chance to go to both sides with higher likelihood that intervention on either end. But that, forward guidance is going to play a big role because this rho, like, let me tell about the rho, so some small deviations in the rho can make a big difference in how the spillovers actually work. Yeah?
So technically we have 3 minutes left, but for the people who want, they can stay a little bit longer.
Oh, no. Okay, so let me try to be quick here. Okay, so this is the network. So this is basically the path of rho. Okay, so this is the path of rho where I don't control for any fundamentals. Okay, so this is just the time series representation of the time variation. Okay, so you see that on average it's pretty high. I mean, it's actually also pretty volatile. And then, we have these recession dates because we're trying to understand like what exactly does this time variation relate to, but perhaps it relates to liquidity. We should actually look into this. Okay, so then we add in these controls saying, we'd like to have some interpretation, or we would like to bring this third dimension of monetary policy into the mix. So, we have the forward guidance from Gurkaniak, Sak, and Swanson, and then IP growth and market uncertainty. Okay, so these are the parameter estimates, and then we are going to do a model selection exercise. So essentially the model preferred by AIC is the model 2, where you actually control for the path vector. So once you add this other macro stuff, it doesn't seem like this is actually helping. Given that, I mean, so Sylvia, this is probably the better way to summarize the model, as you were alluding to. So the notion of impact impulse response, okay? So again, like there are numbers on the x-axis, but these are not time series horizons, okay? So this is like number of rounds it's going to take for the model to converge, so you can think about it as contemporaneous adjustment, yeah? Like in some sense, I mean, what we're plotting here is very similar to this textbook notion of Keynesian multipliers, right? So that's kind of how we teach the undergrads. So this is essentially what we have on the slides. So let me tell you what's going on. So this is if you shock the 3 months origin, 6 months origin, 1 year origin. So if you are the monetary policy authority, somehow if you manage to generate a surprise in 3 months and not anywhere else, right? I mean, so this is the exercise we have. And then you have the different maturities in different colors. So the green greens are the short end, so 3 months, 6 months. The blues are the medium run, so 1 year, 2 year, 5, and then the red is the long run. Okay, so rho is also changing over time, so I could show you 3-dimensional plots, which are very hard for me to read, so I decided to do a 2-dimensional one. So this is conditioned on the average intensity. So rho is fixed at whatever is the sample average that we get. So what do we get here is that given this average intensity, I mean, intervention in the short end essentially stay in the short end. Interventions in the medium end. So this is kind of the question that Sylvia, you were asking. So if I shock the 3 months, right, it sort of stays there. But if I shock the 1 year, it also moves up the short end. Yeah. And then, I mean, you can go through this thing. And if you shock the long end, it also stays compartmentalized on the long side of the yield curve. So from here, I mean, essentially was my conclusion that the interventions on the medium run actually has a chance to go on both sides of the yield curve with a higher likelihood. This intensity matters quite a bit. So if I actually condition on the minimum intensity, and again, on a, you know, this was kind of clustered on a or moving around on a high value, right? So if I actually condition on the minimum intensity, I mean, the results are very different, you know. So here, like, you actually really compartmentalize the effect of the surprises. And if you do the maximum, basically everything moves together. Okay, so little changes in the value of rho, I mean, that actually can change the dynamics of this contagion or propagation or spatial response, or however you would like to refer to this. So the other thing that is interesting is that, you know, the magnitude of the surprise also matters. So this is still average intensity, and this is the 25 basis point. And you see here, like, basically everything moves. So, you know, smaller surprise given the average intensity actually can have a different effect than the larger surprise. Okay, so then this is perhaps a final graph, but perhaps the most interesting one. So what's nice about this is that I can do exercises like this operation twist episodes, right, where there are interventions on both sides of the yield curve, and then you can try to see what exactly happens in the, you know, on the end of the spillovers. So let me tell you the figure. So this is 1 basis point intervention in 3 months, and then -5 basis points on the 10-year, given that you know, rho equal to 0.95, so average intensity. So this is the same thing, but now given like minimum intensity. This is now similar thing, like the size of the surprise is a little bit higher on the 3 months end. And then here, what if, you know, this is parallel to this figure, but what if you intervene on the 6 months, you know, not on the 3 months, but you actually intervene on the 6 months. So you see, like, you know, makes a big difference. So this, if you intervene on the 3 months at the end, like the short end is down. So surprise was positive on the short end and then negative on the long end. But you know, the multiplier, if you will, implies that they all go down. Yeah. If you intervene on the 6 months, on the other hand, you actually have a chance to push up the short end, and then the long end goes down. So it essentially does whatever you were hoping to do with operation twist. You know, and then now we have like a similar exercise where you intervene on the 1-2 year. So this essentially exercises somehow targeted to what actually happened in the market on the operation twist episode, helps perhaps appreciate the different aspects of things that we are considering, in that, you know, the maturities, there's first the asymmetry is important. So I don't want to impose symmetry to start with. And then, you know, there is some trade-off between where do you intervene as a central bank, and then, you know, how do you amplify or move around this network intensity with communication or, you know, the newer tools of monetary policy. So the bottom line, you know, if you summarize all these figures, and there are more in the paper, is that essentially the medium run is more connected. The medium maturities are more connected to the rest than either end of the yield curve. So as a policymaker, maybe that's an important thing to have in mind. And I think I'll conclude, maybe I'm not super over time. Okay, so basically introduce this unknown and potential asymmetric weights into this class of models in the dynamic spatial lag literature. So simulations are promising. We feel comfortable with this, but also I think our exercise, I mean, I personally think our exercise to monetary policy is pretty interesting and innovative. If you guys think like we can apply this in other contexts, please, or let us know. And some further things, again, so this was discussed. So for higher dimensions, perhaps like, we should think of some simulation-based approaches to actually handle this. I think that's
Thank you so much, Tatevik, and thank you, Julia, also.